Welcome to the deep dive. Today we're tackling a big one, a real classic. Stephen Hawking's A Brief History of Time.
Yeah. Published back in '88, wasn't it? Hard to believe it's been that long.
It really is, and it had such a massive impact. So our mission today is to journey through Hawking's view of the cosmos, origins, black holes, time itself. We want to pull out the key insights, the really surprising stuff from the material you sent over.
Definitely. And Hawking jumps right into those huge questions, the ones people have asked forever. Like,
Yeah.
where did everything come from?
Yeah.
Does the universe have a beginning, an end? What even is time? Can we know it all?
Yeah.
And he shows how physics isn't just philosophy anymore. It's actively digging into these mysteries. It's become an experimental science, in a way.
Okay, so maybe let's start with the history, how we even got to Hawking's point of view. For ages, the picture was, well, pretty
Oh,
different.
absolutely. Think ancient Greeks, Aristotle, Ptolemy.
Yeah.
They saw this static universe with Earth right smack in the middle, geocentric.
Everything revolving around us, and that idea stuck for a long time.
Until people like Copernicus and Galileo came along.
Right. They really shook things up. Putting the sun in the center, heliocentrism, that wasn't just moving furniture around. It changed everything about how we saw our place.
And that paved the way for Newton, Isaac Newton. He brought the math.
The laws of motion, gravity, suddenly the universe seemed predictable, like a giant clockwork machine.
Exactly. You could calculate the orbits, predict eclipses. It was incredibly powerful. A huge leap.
But even Newton's amazing system had, well, cracks, right? And didn't quite explain light perfectly or what gravity was doing at really tiny scales.
Precisely. It worked brilliantly for planets and apples falling from trees, but struggled with the very small and the very fast, like light. It wasn't the complete picture.
Which sets the stage for the next giant leap, Albert Einstein.
Einstein, yeah. His theories of relativity just fundamentally changed the game. Space, time, gravity, he rewrote the rule book.
And this is where it starts to feel a bit sci-fi, almost. Einstein's big idea. Space and time aren't separate things.
No, they're woven together, this four-dimensional space-time. That's the stage.
But it's not just a passive stage, is it?
Not at all. That's the key. Mass and energy actually warp it, curve it.
So gravity isn't some mysterious force pulling things.
Exactly. It's the curvature. Think of that bowling ball and rubber sheet analogy. Things follow the curves caused by heavy objects. That's gravity, according to Einstein.
Okay, and this leads to some really weird consequences, stuff Hawking built on, like time itself isn't constant.
Nope. It slows down near massive objects. Clocks literally tick slower, closer to a strong gravitational field. It's been measured, actually. Tiny effects, but real.
Wow. And the other huge thing is the universe expanding. We can see galaxies moving away from us.
Which implies, if you run the movie backwards,
Everything must have started from a single point, a beginning.
the Big Bang, that's the name we give it, roughly 13.8 billion years ago. A hot, dense beginning for everything.
And we have evidence for this, right? It's not just a nice idea.
Oh, yeah. Good evidence. The redshift of distant galaxies, their light is stretched, like that siren sound-changing pitch.
As they rush away.
And the cosmic microwave background radiation, this faint afterglow, leftover heat from that initial explosion, filling all of space.
Okay, but then the massive question comes up. If it all started then, what about before the Big Bang?
That's where things get really tricky. Our best theories, general relativity for gravity and quantum mechanics of the small stuff, they just don't work together at that point.
They break down.
Completely. At that singularity, the math gives nonsense answers. We can't describe before the Big Bang with current physics. We need something more, some kind of unified theory.
So the very beginning is still a mystery. And what about the end? Does it collapse back in a big crunch or just expand forever?
That's another huge open question. Depends on things like the total amount of matter and energy, the shape of space. Physics has models, different possibilities, but we don't know the final answer yet. Could expand forever, getting colder and emptier, or maybe something else entirely.
Okay, so that sets up Einstein's universe. Then Hawking really dives into one of the weirdest parts, black holes.
Yeah, his work on black holes was truly revolutionary. Before him, the thinking was, they just suck everything in, nothing escapes, one-way street.
Light can't even get out, hence black.
Right. But Hawking brought quantum mechanics into the picture, and he showed something incredible. Black holes aren't perfectly black,
Weak.
in a sense. They emit radiation very slowly due to quantum effects near the event horizon. We call it Hawking radiation now.
And this means they can actually shrink? And maybe even disappear eventually.
Exactly. They can evaporate over immense timescales. This was a mind-blowing idea.
What does that mean, though, for physics?
Well, it causes a big headache, actually, the information paradox. Quantum mechanics says information about what makes up an object can't truly be destroyed. But if a black hole swallows stuff and then evaporates into random radiation, where does the information go?
Oh, I see. It seems like it's just gone, which clashes with quantum rules.
Precisely. It's a deep conflict between general relativity and quantum theory, and physicists are still arguing about it. It's a major driver for finding that unified theory we mentioned.
And Hawking didn't just stop there. He explored even wilder ideas, right? Stuff that sounds like pure science fiction.
He did. He talked about wormholes, for instance, theoretical tunnels through spacetime.
Shortcuts across the universe. Or even time.
Potentially, yes, allowed by relativity in theory. But building one would require exotic matter with negative energy density, stuff we've never seen and might not even exist.
So probably not happening anytime soon. What about time travel itself?
Again, relativity doesn't strictly forbid it under certain conditions, like near rotating black holes or using wormholes. But the practicalities seem, well, insurmountable. You run into paradoxes, the need for impossible materials.
And parallel universes. Did he touch on that?
Some interpretations of quantum mechanics, like the many worlds idea, suggest that every quantum measurement splits the universe into multiple branches. Hawking discussed these possibilities.
Wow. So multiple versions of reality existing alongside ours.
It's a fascinating interpretation, helps resolve some quantum weirdness, but again, highly speculative. We have no way to test it currently. These are ideas at the very edge of theoretical physics.
So zooming out a bit, we have these two incredibly successful theories. General relativity for the big stuff, quantum mechanics for the tiny stuff. But they don't mesh.
That's the core problem in fundamental physics today. They describe different aspects of reality brilliantly, but they clash in extreme situations like the Big Bang or inside black holes. They speak different languages almost.
And the big goal is to find a single theory that combines them, a theory of everything.
Exactly. A unified framework that describes all forces, gravity, electromagnetism, the nuclear forces, and all matter from a single set of principles. That's the dream.
Are there candidates, theories people are working on?
Oh, yes. String theory is probably the most famous one. It suggests fundamental particles are actually tiny vibrating strings.
Strings?
Yeah. Different vibrations correspond to different particles. It potentially unifies gravity and quantum mechanics, but it requires extra spatial dimensions and is very hard to test experimentally.
In quantum gravity, is that different?
It's more of a general approach, trying to apply quantum principles to gravity directly. Loop quantum gravity is one example. These are all works in progress, though. Deeply mathematical and complex.
But Hawking seemed optimistic, didn't he? That we would find it eventually.
He was. He had this deep faith in human reason. He felt discovering this ultimate theory wouldn't just be a scientific triumph. It would be something more profound.
Which brings us back to why A Brief History of Time resonated so much. It wasn't just explaining physics, was it? It was about something bigger.
Absolutely. It tapped into that fundamental human desire to understand where we came from, what the universe is. It showed the power of our minds to grapple with these enormous concepts.
He makes it feel like anyone can participate in that quest for understanding.
Exactly. That famous closing line of the book.
Oh, yeah.
He says, basically, if we find a complete theory, then everyone, scientists, philosophers, just ordinary people, could take part in the discussion of why we in the universe exist. It would be, in his words, the ultimate triumph of human reason, for then we would know the mind of God.
Wow. That's a powerful thought. It's an invitation, really.
It is an invitation to wonder, to ask questions, to not be intimidated by the scale of the universe, but to engage with it.
So wrapping this up, the big takeaway seems to be the universe is incredibly vast, incredibly strange, often beautiful, but maybe not fundamentally unknowable.
Right. And that we humans, despite being small specks, have this amazing capacity to figure things out, to piece together the cosmic puzzle.
So final thought maybe for you listening. Think
Yeah.
about how this journey of discovery continues.
Yeah, consider how each generation builds on the last. Science lets us see a little bit further, understand a little bit more. It constantly reshapes how we see ourselves and our place in this vast, amazing cosmos as an ongoing story.